TAN 618 should not exist. Roughly 10.4 billion light-years from the chair you are sitting in, there is a mouth in space, a literal region where matter falls inward forever and never returns, the largest black hole humanity has ever confirmed, 66 billion times the mass of our Sun, old enough to have formed when our universe was still a child. And at this very moment, something from TAN 618 is traveling toward Earth. Something that has been on its way for more than 10 billion years. Something that in a very real way has already arrived. Whether that should worry you is what the rest of this video is going to answer, but not yet. Because to understand what is happening right now between that ancient monster and this planet, you first need to understand what TAN 618 actually is. In 1957, two astronomers at a Mexican observatory pointed their telescope at what they thought was a faint blue star. It wasn't. What they had found was a quasar, a beacon shining with the light of 140 trillion suns, powered by something so massive that physicists had to invent a new category of black hole just to describe it: ultramassive. A word that didn't exist until objects like this forced us to create it. And here is the part that keeps cosmologists awake at night. TAN 618 is old. So old that when its light began its journey to Earth, the universe itself was barely 3 billion years old, which means this object had already grown to 66 billion solar masses before most galaxies had even finished forming. That is not supposed to be possible. Every model we have for black hole growth says it takes time, billions of years of feeding, of collisions, of slow accumulation. TAN 618 had none of that time. And yet there it sits, impossibly large, impossibly early, shining across half the observable universe like a fact that refuses to behave. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. There is a hole in space so large that if you fell toward it, you would have time to live an entire second life before you reached the point of no return. You could be born, grow up, fall in love, raise children, retire, and die of old age, all while drifting toward the edge. And even then, you would only be approaching the boundary, not the center, just the edge, the boundary where physics stops negotiating. This is not a metaphor. This is TAN 618, and it weighs 66 billion times more than our Sun. 66 billion. Say that number out loud. Let it sit in your mouth for a second, because your brain is going to try to skip past it. It is going to try to file it away in the same mental drawer where you keep other big numbers that don't mean anything. The national debt, the number of stars in the galaxy, the number of grains of sand on all the beaches on Earth. Your brain wants to treat them all the same, as background noise, as quantities too large to matter. Do not let it. 66 billion suns, not metaphorical suns, not sun-sized units of measurement, actual stars like the one you woke up under this morning, compressed into a region of space so dense that it has torn a hole in the fabric of reality itself. A hole so deep that nothing, not light, not time, not information of any kind, can climb back out once it falls past a certain line. That line, that edge, that point of no return is called the event horizon. And for TAN 618, the event horizon is not a tight little knot of warped space tucked away somewhere distant and theoretical. It is a sphere with a diameter of roughly 390 billion kilometers. If you are looking for something to compare that to, stop. There is nothing in your daily experience that will help. The distance from the Earth to the Sun is about 150 million kilometers. That is what we call one astronomical unit. 1 AU. It is the ruler we use to measure the solar system. Pluto, the outermost major object we still bother to name, orbits at about 40 AU. The edge of the Oort cloud, the shell of icy debris that marks the true outer boundary of the Sun's influence, sits at around 100,000 AU. TOEN 618's event horizon spans roughly 2,600 AU. You could fit our entire solar system inside it, Sun to Pluto, and still have room for dozens more solar systems stacked end to end. You could throw in the Oort cloud, the Kuiper belt, every comet, every asteroid, every speck of dust that has ever felt the Sun's gravity, and it would all vanish into a region that does not even reach halfway to the edge. Light itself, the fastest thing in the universe, the thing that crosses the space between Earth and the Moon in 1¼ seconds, would take roughly 2 weeks to travel from one side of TOEN 618's event horizon to the other. 2 weeks, not 2 weeks to reach the center. 2 weeks just to cross the boundary. Think about what that means. If you were somehow standing on one side of the event horizon with a flashlight, which you could not do because you would be dead in more ways than physics has names for, and you shined that flashlight across to the other side, the light would not arrive for 14 days. It would spend 2 full weeks crossing nothing but empty space inside the boundary of a single object. That is not a black hole in the sense most people imagine when they hear the term. That is not some collapsed star sitting quietly in the dark, minding its own business. That is a wound in space, a scar, a feature of the universe so extreme that it sits outside the fando of things we have everyday language for. Astronomers do not call objects like TOEN 618 stellar mass black holes. Those are the normal ones. The kind that form when a massive star runs out of fuel, collapses, and leaves behind a core so dense that it punches through the bottom of reality. Stellar mass black holes weigh anywhere from a few times the mass of the Sun to maybe a few dozen solar masses. They are common. The Milky Way is littered with them. We have detected dozens. We expect millions more are out there, quietly orbiting, occasionally feeding, doing the things black holes do when no one is watching. We also do not call TOEN 618 a supermassive black hole. Supermassive black holes live at the centers of galaxies. Our own Milky Way has one. It is called Sagittarius A star, and it weighs about 4 million times the mass of the Sun. For a long time, that seemed like the upper end of the scale. Big, yes, impressive, certainly, but still within the boundaries of what models predicted. A galaxy the size of ours, with hundreds of billions of stars, would naturally accumulate a black hole weighing a few million solar masses at its core over billions of years. The math worked, the observations matched, everything fit. Then we found bigger ones. M87, the giant elliptical galaxy that gave us the first direct image of a black hole in 2019, has a supermassive black hole at its center weighing about 6.5 billion solar masses. That image, the glowing orange ring with a dark center that circulated across every news site on the planet, was not a photograph of the black hole itself. It was a photograph of the light from superheated gas swirling around it at nearly the speed of light, tracing the shape of the event horizon in silhouette. 6.5 billion solar masses. That was stunning. That was at the edge of what seemed reasonable. TOEN 618 weighs 10 times that. It weighs so much that astronomers had to invent a new term for it. They call it an ultramassive black hole. Not super, ultra, because the prefix super had already been used and it was no longer adequate. The scale had moved past the vocabulary. Ultramassive black holes, as a category, are objects that weigh more than 10 billion solar masses. TOEN 618 sits comfortably at the top of that list. There are a handful of other candidates that come close. Holmberg 15A, Phoenix A, IC 1101. Objects with names that sound like database entries because that is essentially what they are. Catalog numbers assigned to things so far away and so extreme that no one bothered to give them proper names. But even among that group, 20N618 stands out. Not just because it is the heaviest, but because of when it existed. The light we see from 20N618 today left that object 10.8 billion years ago. The universe itself is 13.8 billion years old, so we are seeing TON 618 as it was when the cosmos was only 3 billion years old, a toddler universe, an infant cosmos still figuring out how to build galaxies, still cooling down from the Big Bang, still in the messy early phase where the rules were supposed to be different, and yet there it is, already a giant, already fully formed, already weighing 66 billion times more than the Sun, when stars themselves had barely begun to populate the universe. That is the part that does not fit. Black holes grow in two ways. They eat or they merge. Eating happens when a black hole pulls in gas, dust, stars, anything that drifts too close. The material does not fall straight in, it spirals. It forms an accretion disk, a swirling flat plane of matter that heats up through friction as it accelerates toward the event horizon. The hotter it gets, the brighter it glows. At a certain point, the disk gets so hot that it radiates more energy than entire galaxies. That glow is how we detect black holes at cosmic distances. We cannot see the hole itself. We see the light from everything it is about to destroy. The second way black holes grow is by merging. When two black holes collide, they combine. The process is violent. It releases gravitational waves, ripples in space-time that we can now detect with instruments like LIGO and Virgo. The resulting black hole is roughly the sum of the two that merged. Do that enough times and you can build something very large. The problem is time. Eating has limits. There is a theoretical maximum rate at which a black hole can feed, called the Eddington limit. Push past that rate and the radiation pressure from the infalling material becomes so intense that it blows away anything trying to fall in. The black hole chokes on its own meal. Feeding at the Eddington limit, a stellar mass black hole starting at 10 solar masses can double its mass roughly every 50 million years. Sounds fast. It is not. Run that growth curve from the formation of the first stars, maybe 200 million years after the Big Bang, all the way forward to when TON 618 is shining at us, and you do not get 66 billion solar masses. You do not even get close. Mergers help, but mergers require black holes to find each other. And in the early universe, space was big and black holes were rare. Even if every black hole in a young galaxy somehow found every other black hole and merged in rapid succession, which is wildly optimistic, the timeline still does not close. Run every plausible combination of feeding and merging that physics allows. Use the most aggressive assumptions, squeeze every possible advantage out of the models, and the answer you get is that TON 618 should not weigh 66 billion solar masses at the age we are seeing it. It should weigh maybe a few billion, maybe 10 billion if you push the parameters to the breaking point. But 66 billion? No. That is not supposed to happen, and yet it did. Standing here 13.8 billion years after the Big Bang, looking backward across 10.8 billion light-years of space, we see an object that by every rule we have written down should not exist, not as a violation of physics. Physics does not care what we think is reasonable. As a violation of time, there simply was not enough of it. TON 618 is not the only one, by the way. It is the largest, but it is not alone. Astronomers have been finding massive black holes at high redshifts. meaning very far away, meaning very early in the universe's history, for years now. And every time they find one, the models get a little more uncomfortable, because the models were built on assumptions about how long things take, how long it takes for stars to form, how long it takes for those stars to collapse into black holes, how long it takes for those black holes to eat enough material to grow, and the universe keeps handing us objects that appear to have skipped steps. TON 618 is the headline case, the one that forces the conversation, the one that sits at the edge of the data like a fact that refuses to behave. If you could somehow observe TON 618 up close, not that you would survive the attempt, you would not see a black sphere, you would not see an object at all. What you would see is absence, a perfectly circular region of nothing where the stars behind it should be. And around that nothing, you would see a ring, not a solid ring. A smeared, distorted halo of light from every galaxy in the universe behind you, bent and stretched by gravity so extreme that space-time itself curves into a lens. The sky would not look like a sky. It would look like a funhouse mirror wrapped into a circle. And at the center, where the black hole waits, there would be a darkness so complete that your brain would struggle to process it as a surface or a depth, or anything with a name. That is what TON 618 is. That is the thing we found sitting in the early universe, already grown, already shining, already breaking the rules we thought we understood. And the question it raises is not just how did this happen? The question is, what else did we get wrong? Because if something this massive can exist this early, then the assumptions we have been using to model the history of the universe are not just slightly off. They are missing something fundamental, something about how black holes are born, something about how they grow, something about the conditions in the infant cosmos that we have not accounted for. TON 618 is not just an object, it is a message, a signal from the early universe telling us plainly that the story we have been telling ourselves is incomplete. The largest black hole ever found, sitting in an era when it should not have had time to grow, shining so brightly that we can see it across more than 10 billion years of cosmic history. And it all started with a mistake. A misidentification on a photographic plate in Mexico in 1957. A faint blue smudge that no one thought was anything special, that someone catalogued as star number 618 on a survey list and then forgot about, until 15 years later, when someone looked again. The discovery of TON 618 was an accident. Not in the sense that someone tripped over a telescope and accidentally pointed it at the right patch of sky, but in the sense that nobody was looking for what they found. Nobody in 1957 was hunting for the largest black hole in the universe. Nobody even knew black holes existed yet. The term would not enter the scientific vocabulary for another decade. What they were looking for was stars, ordinary stars, the kind you can catalogue, measure, and forget about. The year was 1957. The location was the Tonantzintla Observatory, a modest facility perched on a hill about 2 hours southeast of Mexico City. The observatory had been built in 1942, and by the late 50s it was running a long-term photographic survey of the northern sky. Two astronomers, Braulio Iriarte and Enrique Chavira, were working their way through plate after plate of long-exposure images, marking down anything that looked unusual. Bright stars, variable stars, objects with strange colors, anything that stood out against the background hum of the cosmos. On one of those plates, they found a faint blue point of light. It was not dramatic. It was not bright. It did not pulse or flicker or do anything particularly interesting. It was just there, a tiny blue smudge sitting quietly in a field of other tiny smudges. They catalogued it as entry number 618 on the Tonantzintla survey list, TON 618. And then they moved on. For 15 years, that is all it was, a number in a catalogue, a footnote in a survey that most astronomers would never read. If you had asked anyone in 1957 what TON 618 was, the answer would have been simple. A faint blue star, probably unremarkable, probably not worth a follow-up observation, move along. But in the late 1960s, something changed. Radio astronomy had matured. Telescopes that could detect radio waves instead of visible light were scanning the sky, and they were finding objects that did not make sense. Bright radio sources that, when cross-referenced with optical surveys, corresponded to what looked like ordinary stars. Except they were not ordinary. When astronomers pointed spectrographs at them, instruments that split light into its component wavelengths, the spectra did not look like starlight. They looked alien. Broad emission lines, extreme redshifts, light that had been stretched by the expansion of the universe to the point where ultraviolet emission was arriving in the visible range, or even the infrared. These objects were not stars. They were something new, something no one had predicted. And because they looked star-like but clearly were not, astronomers gave them a name that reflected the confusion: quasi-stellar radio sources. The term got shortened. Quasars, TON 618, ended up on that list. Someone, and the historical record is frustratingly vague about exactly who and exactly when, went back and looked at the faint blue star from the Tonant-Sintler survey. They pointed a spectrograph at it, and what came back was not the clean, simple spectrum of a normal star. It was the unmistakable signature of a quasar, a massive redshift. Emission lines that had been Doppler shifted so far toward the red end of the spectrum that the object had to be billions of light years away, not a nearby star, not even a nearby galaxy. A beacon shining from an era when the universe was less than a quarter of its current age. The realization must have been disorienting. Imagine cataloging what you think is a dim light bulb in your neighborhood, and then discovering years later that it is actually a searchlight on the other side of the planet, so bright that you can see it from thousands of miles away. That is the scale of the misunderstanding. TON 618 was not faint because it was weak. It was faint because it was unimaginably far away. And if it was that far away and we could still see it, then it had to be shining with a luminosity that defied every intuitive sense of what an object in space should be capable of. The numbers, when they finally came in, were obscene. TON 618 is radiating energy at a rate roughly 140 trillion times greater than our Sun. 140 trillion. That is not a typo. That is not an exaggeration. That is the actual calculated luminosity of the object based on its distance and the amount of light reaching Earth. To put that in perspective, our Sun produces about 3.8 times 10 to the 26th watts of power. It has been doing that for 4.5 billion years. It will keep doing it for another 5 billion. The Sun is not a weak object. It is a sustained thermonuclear explosion held together by its own gravity, burning hydrogen into helium at a rate of about 600 million tons per second. That is normal. That is what stars do. TON 618 produces about 5.4 times 10 to the 40th watts. That is 14 orders of magnitude brighter. If you tried to count from the Sun's luminosity up to TON 618's luminosity 1 unit at a time, you would run out of breath, you would run out of years, you would run out of civilizations rising and falling before you got halfway there. Here is another way to think about it. The Milky Way galaxy contains somewhere between 200 and 400 billion stars. Most of them are smaller and dimmer than our Sun, but some are larger and brighter. Average it all out and the Milky Way produces a total luminosity of around 5 billion times the Sun's output. That is every star in the galaxy combined. Every red dwarf, every sun-like star, every blue giant, every supernova remnant still glowing, all of it added together into one number. TON 618, by itself, outshines the Milky Way by a factor of about 28,000. One object, one point source, brighter than 28,000 galaxies like ours placed side by side. That level of brightness requires an engine, not a chemical engine, not even a nuclear engine in the way stars burn fuel. You cannot get that much energy from fusion. There is not enough hydrogen in a galaxy to sustain that output through ordinary stellar processes. The only known mechanism that can produce luminosity on that scale is gravity. Specifically, the gravity of a supermassive black hole feeding on an accretion disk. This is what a quasar actually is. It is not a star. It is not even a type of galaxy. It is the core of a galaxy in a specific phase of its life when the central black hole is actively feeding. Matter, gas, dust, entire stars, anything that drifts too close, spirals inward. It does not fall straight in. Gravity and angular momentum force it into a flat spinning disk around the black hole. As the material spirals closer, it accelerates. Friction between particles in the disk heats the gas to millions of degrees. At those temperatures, the gas glows, not in visible light, in X-rays, in ultraviolet, in every high-energy wavelength the electromagnetic spectrum allows. The result is a disk of superheated matter orbiting a black hole at a significant fraction of the speed of light, radiating more energy than an entire galaxy of stars. That disk is what we see when we look at TON 618. We are not seeing the black hole itself. Black holes do not emit light. We are seeing the light from everything the black hole is about to devour, the last desperate scream of matter before it crosses the event horizon and disappears forever. That glow is so bright that it drowns out the entire galaxy around it. TON 618 sits at the center of a galaxy. It has to. Black holes this massive do not form in isolation. They grow at the centers of galaxies over billions of years, fed by gas funneled inward by the galaxy's gravitational well. There are stars around TON 618, billions of them, maybe hundreds of billions. A whole galaxy's worth of ordinary stellar population going about their business, orbiting the core, living and dying the way stars do. We cannot see any of them. The quasar is too bright. It is like trying to spot a firefly hovering next to a stadium floodlight. The light exists, but it is completely overwhelmed. For decades, astronomers assumed quasars were isolated objects, lone beacons in empty space. It was not until imaging technology improved in the 1980s and 90s that we started resolving the faint fuzz of host galaxies around some of the nearer quasars. TON 618 is too far away for that. The host galaxy, if we could see it, would be a faint smudge buried under the glare of the active nucleus. So we point our telescopes at it, and all we see is the point, the brilliant blue-white point of a black hole feeding at a rate that converts mass into energy with terrifying efficiency. The discovery of quasars in the 1960s was one of the most disruptive events in the history of astronomy. It forced scientists to accept that the universe contained objects far more extreme than anything predicted by theory. Before quasars, the assumption was that the brightest objects in the universe were galaxies, large collections of billions of stars shining together. That made sense. It fit with everything we knew about how gravity assembled matter and how stars produced light. Then quasars showed up and broke that assumption. Here were objects that looked like stars but were outshining entire galaxies. Objects so distant that their light had been traveling for billions of years. Objects that required a completely new model to explain. The idea that supermassive black holes could exist, that they could grow to millions or billions of solar masses, that they could power emission bright enough to be seen across most of the observable universe, was not on anyone's bingo card in 1960. TOE N618 was part of that revolution. Not at the beginning. It was not one of the first quasars discovered. That honor goes to 3C273, identified in 1963 by Martin Schmidt, but TOE 618 ended up being one of the most extreme examples. When astronomers started compiling lists of the brightest, most distant, most energetic quasars, TOE 618 kept showing up near the top. And as measurement techniques improved, as redshift estimates got more precise, as models of black hole masses got more sophisticated, the numbers attached to TOE 618 kept climbing. By the early 2000s, it was clear that this was not just a bright quasar. It was one of the most luminous objects ever detected, and the black hole powering it was not just supermassive, it was in a category by itself. Estimates of the black hole's mass vary depending on the method used, but the consensus range sits between 40 and 66 billion solar masses. Some papers cite the lower end, others cite the higher end. The uncertainty comes from the fact that we cannot directly measure the mass of a black hole 10 billion light-years away. We have to infer it from the light we see. The technique most commonly used is called reverberation mapping. You measure the broad emission lines in the quasar's spectrum, lines produced by gas clouds orbiting the black hole at high speed. The width of those lines tells you how fast the gas is moving. The brightness variations in the quasar's light tell you how long it takes for changes in the central engine to propagate outward to the surrounding gas clouds. Combine the velocity with the light travel time, and you can estimate the size of the region where the gas is orbiting. From that, using Kepler's laws, you can calculate the mass of the central object. It is not a perfect method. It relies on assumptions about the geometry of the gas clouds, the inclination of the disk, the stability of the emission over time. Different assumptions give different masses, but even the most conservative estimates put TOE 618's black hole at 40 billion solar masses. The more aggressive estimates push it past 66 billion. Either way, it is the largest confirmed black hole we have ever found. The discovery was accidental in the best possible way. Nobody set out to find the biggest black hole. They set out to catalogue stars. They found a faint blue point. 15 years later, someone looked closer and realized the point was not a star at all. It was a signal from the other side of the universe, a signal so bright that it had been traveling for over 10 billion years and was still strong enough to register on a photographic plate in Mexico. There is something almost absurd about that. The universe is unimaginably large. The number of stars, galaxies, black holes, planets, moons, asteroids, clouds of gas, all of it scattered across billions of light-years of space, is so vast that the odds of any one object standing out are effectively zero. And yet here was TOE 618, sitting quietly in a corner of the sky, not moving, not calling attention to itself, just shining so brightly that a telescope in Mexico in 1957 caught a tiny fraction of its light on a piece of film, and decades later someone realized what they were looking at. If the survey had been slightly less thorough, if the photographic plate had been slightly less sensitive, if the follow-up spectroscopy had been delayed by another decade, TOE 618 might still be sitting in a catalogue somewhere labeled as star number 618, a footnote, a number, nothing special. Instead, it became a cornerstone, a reference point. The object astronomers point to when they need an example of how extreme the universe can get when it really tries. The brightest quasar, the largest black hole, the thing that should not exist but does. And the question it raises, the one that no amount of luminosity measurements or spectroscopic analysis can answer, is how. How does a black hole grow that large that fast? How does an object weighing 66 billion times the mass of the Sun end up fully formed in an era when the universe itself was barely 3 billion years old, when the first galaxies were still assembling, when the conditions for building something that massive should not have existed yet? Shouldnt 618 is shining at us from an impossible moment in cosmic history, a moment when the rules say it should not be there. And yet there it is, a beacon in the dark, a signal from the infant universe, a message written in light that has been traveling toward Earth for longer than our planet has existed. And the message says very clearly that something about the story we have been telling ourselves is wrong. The universe was 3 billion years old when the light we see from Shouldnt 618 began its journey. 3 billion years. That sounds like a lot of time. It is not. 3 billion years after the Big Bang, the cosmos was still in its adolescence. Galaxies were smaller, messier, less organized than the grand spirals and ellipticals we see today. Stars were being born at a furious rate in chaotic bursts of star formation that would never be repeated in later epochs. The universe was hotter, denser, more volatile. It was a universe still figuring out how to build the structures that would one day include planets and moons, and eventually things like you sitting in a chair watching a video about black holes. And somewhere in that young universe, Shouldnt 618 already existed, not as a faint newborn, not as a modest seed struggling to grow, as a fully formed monster weighing 66 billion times the mass of our Sun, already feeding, already shining, already one of the brightest objects in the entire cosmos. That timeline is the problem. To understand why, you need to know how black holes grow. Because black holes do not spring into existence at 66 billion solar masses. They start small, or at least they are supposed to. There are two main ways a black hole can gain mass. The first is accretion. The black hole pulls in material from its surroundings, gas, dust, stars, anything that drifts too close. That material does not fall straight in. Conservation of angular momentum forces it into a spinning disk around the black hole. The disk heats up through friction as particles collide and spiral inward. Eventually, the matter crosses the event horizon and adds its mass to the black hole. Repeat that process over millions or billions of years, and a black hole that started at 10 solar masses can grow to 10,000, 10 million, maybe even 10 billion. The second way is mergers. When two black holes collide, they combine. The process is not gentle. It releases gravitational waves, ripples in the fabric of space-time itself that we can now detect with observatories like LIGO and Virgo. The resulting black hole weighs roughly the sum of the two that merged, minus a small amount of mass that gets radiated away as gravitational wave energy. If black holes merge often enough, and if galaxies collide and bring their central black holes together, you can build something very massive over time. Both of these processes work. We have observed them. We have detected gravitational waves from merging black holes. We have watched accretion disks glow around supermassive black holes in nearby galaxies. The physics is solid. The models are well tested. They explain the 4 million solar mass black hole at the center of the Milky Way. They explain the 6.5 billion solar mass black hole at the center of M87. They explain the population of supermassive black holes that astronomers have catalogued across the universe. They do not explain Shouldnt 618. The issue is time, or more specifically, the lack of it. Let us start with accretion, because that is usually the dominant growth mechanism. A black hole sitting at the center of a galaxy has access to a lot of gas. Galaxies in the early universe were especially gas-rich, loaded with the raw material for star formation and black hole feeding. So in principle, a black hole in that environment should have no trouble finding something to eat. The problem is how fast it can eat. There is a theoretical speed limit on black hole growth called the Eddington limit. It is named after Arthur Eddington, the British astrophysicist who first worked out the math in the early 20th century. The Eddington limit describes the point at which the outward pressure from radiation produced by infalling matter exactly balances the inward pull of gravity. Here is why that matters. When material falls toward a black hole and heats up in the accretion disk, it radiates energy, a lot of energy. That radiation exerts pressure on the surrounding gas, pushing it outward. If the black hole tries to eat too fast, the radiation pressure becomes so intense that it blows away the very material trying to fall in. The black hole chokes. It cannot swallow any more until the pressure subsides. The Eddington limit is not a hard wall. It is more like a speed limit on a highway. You can exceed it briefly under the right conditions. Some black holes probably do. But sustained growth at rates significantly above the Eddington limit is difficult. The radiation pressure does not go away. It pushes back. It disrupts the accretion flow. It turns what should be a steady inward spiral into a turbulent mess where most of the gas gets blown out into space instead of falling in. So let us assume a black hole grows at the Eddington limit. That is the most optimistic scenario, feeding as fast as physics comfortably allows. At that rate, a black hole can double its mass roughly every 50 million years. Some sources cite 40 million, some cite 60 million. The exact number depends on the efficiency of the accretion process and the radiative properties of the gas. But 50 million years is a reasonable middle estimate. Now run the numbers. The first stars in the universe formed somewhere around 200 million years after the Big Bang. Maybe a bit earlier, maybe a bit later. Current models put the range between 100 and 250 million years. Those first stars were enormous, hundreds of times more massive than our Sun, burning hot and fast. They lived for only a few million years before collapsing into black holes. Let us be generous and say the first black holes formed 200 million years after the Big Bang. Our ONE 618 is seen as it was, roughly 10.8 billion years after the Big Bang. The light we observe left the object at that time, so the black hole had at most 10.6 billion years to grow. From formation to the moment we are seeing it, 10.6 billion years. If a black hole starts at 10 solar masses, which is a reasonable mass for a stellar collapse, and doubles every 50 million years, how big does it get in 10.6 billion years? You get about 212 doublings. 10 solar masses doubled 212 times gives you a black hole weighing about 6 times 10 to the 63rd solar masses. That number is meaningless. It is larger than the number of atoms in the observable universe. Obviously, that is not what happens. The calculation assumes continuous exponential growth at the Eddington limit, with no interruptions, no pauses, no periods where the gas supply runs out or gets disrupted. That is not realistic. Real black holes do not grow smoothly. They go through active phases when gas is available and quiescent phases when it is not. They get feedback from star formation. They get blown clean by supernova winds. They experience periods where mergers stir up their surroundings and periods where nothing much happens. Growth is episodic. Start and stop. Feast and famine. If you account for those interruptions and assume a more realistic duty cycle where the black hole spends maybe 10% of its time actively feeding at the Eddington limit, the numbers change. Now you are looking at doubling times closer to 500 million years. over 10.6 billion years, that gives you about 21 doublings. 10 solar masses doubled 21 times is about 21 million solar masses. That is still nowhere near 66 billion. You can adjust the assumptions. Start with a bigger seed, say 100 solar masses instead of 10. Now you get 2.1 billion solar masses. Still not enough. Start with 1,000 solar masses. Now you get 21 billion. Closer, but 1,000 solar mass seed is already stretching credibility. Stellar mass black holes do not form at 1,000 solar masses. They form at a few solar masses, maybe a few dozen if the progenitor star was exceptionally massive. Getting to 1,000 solar masses requires either a very unusual formation process or a lot of early mergers. And even if you grant that, even if you start with a massive seed and assume aggressive feeding, you still fall short of 66 billion unless you push the parameters into ranges that make astrophysicists uncomfortable. You need near-continuous Eddington-limited accretion with very few breaks. You need a gas supply that never runs out. You need an environment that keeps funneling material inward without disruption for billions of years. And even then, you are cutting it close. Mergers help. If a black hole grows primarily through merging with other black holes, you can leapfrog some of the slow accretion phases. Every time two black holes combine, you add their masses together in one go. Do that enough times, and you can build something very large relatively quickly. The problem is frequency. Mergers require black holes to find each other. In the modern universe, supermassive black holes sit at the centers of galaxies, and galaxies are spread out over millions of light years. Mergers happen when galaxies collide, and galactic collisions are rare. They take hundreds of millions of years to complete. The black holes at the centers of the colliding galaxies spiral toward each other slowly, losing orbital energy to gravitational wave radiation and dynamical friction as they plow through the surrounding stars and gas. The final merger can take another few 100 million years after the galaxies themselves have already combined. In the early universe, galaxies were smaller and closer together. Collisions were more common, so maybe mergers happened more frequently back then. That would help. But you still need a lot of them. To build a 66 billion solar mass black hole primarily through mergers, you need hundreds or thousands of smaller black holes to come together over billions of years. That requires an extraordinarily merger-rich environment. Not impossible, but not typical either. Run the simulations, plug in the most aggressive merger rates that models allow. Combine that with optimistic accretion, and you can get close to explaining TON 618. But close is not the same as comfortable. You are pushing the models to their limits. You are invoking conditions at the edge of what seems plausible. And the result is a black hole that just barely fits within the timeline if you squint and assume everything went right. That is not how science is supposed to work. When you need everything to go right for your model to produce the observed result, that is usually a sign that the model is missing something. So what is missing? Astronomers have proposed several ideas. None of them are proven. All of them require invoking processes that we have not directly observed, but they are the best answers we have for now. The first idea is called direct collapse. In this scenario, a massive cloud of primordial gas in the early universe skips the star formation phase entirely and collapses straight into a black hole. Not a 10 solar mass black hole, 100,000 or even 1,000,000 solar mass black hole. A monster seed. The conditions required for direct collapse are extreme. The gas cloud has to be very massive, very hot and very smooth. Any clumping or cooling would cause it to fragment into stars instead of collapsing as a whole. To keep the gas hot, you need intense ultraviolet radiation from nearby sources to prevent molecules like hydrogen from forming. Molecular hydrogen is a very efficient coolant. It radiates away thermal energy, allowing gas clouds to cool and collapse into stars. Direct collapse only works if you can suppress that cooling. In the early universe, during the first few 100 million years after the Big Bang, conditions might have been right for this in certain rare environments. Intense radiation from the first generation of stars could have kept nearby gas clouds hot enough to undergo direct collapse. If that happened, you would get black holes starting at 100,000 solar masses or more. From there, growing to 66 billion is still a stretch, but the timeline becomes much more manageable. The second idea is runaway stellar collisions. Imagine a very dense star cluster in the core of a young galaxy. Stars are packed so tightly that collisions are common. When two massive stars collide, they merge. The merged star is now more massive and has a larger cross-section, making it more likely to collide with another star. The process runs away. Star collides with star. The merged object collides with another star, and within a few million years you end up with a single monster star weighing thousands of solar masses sitting at the center of the cluster. When that star runs out of fuel, it collapses into a black hole. A very massive black hole. Again, you start with a big seed, and the growth problem gets easier. The third idea is super-Eddington accretion. Maybe the Eddington limit is not as strict as we think. Maybe under certain conditions, black holes can grow faster than the standard models allow. If the accretion flow is very dense and geometrically thick, radiation might get trapped inside the infalling gas instead of escaping and pushing outward. In that case, the black hole could eat much faster without choking on its own light. Some simulations suggest this is possible for brief periods. If TON 618 went through even a few episodes of super-Eddington growth, each lasting a few tens of millions of years, that could boost its mass significantly beyond what standard accretion alone would allow. The fourth idea is just brute force. Maybe 2N618 formed in an unusually rich environment where both mergers and accretion happened at rates far above the cosmic average, a perfect storm of conditions. Lots of gas, lots of black holes, frequent collisions, minimal feedback from star formation or supernovae to disrupt the growth. Everything lined up just right for billions of years. Unlikely, yes. Impossible, no. The universe is big. Rare things happen. Super-Eddington accretion is theoretically possible but hard to sustain, and invoking a perfect storm of conditions is basically admitting that we do not really know. What makes TON 618 particularly frustrating is that it is not alone. Over the past 2 decades, astronomers have found more and more massive black holes at high redshifts. Black holes weighing billions of solar masses sitting in galaxies that formed less than 1 billion years after the Big Bang. Every time a new one is discovered, the models get stretched a little further. Every time the timeline gets tighter. Every time the question gets louder. How did these things grow so fast? The James Webb Space Telescope has made it worse. Webb was designed to see further back in time than any previous telescope, to peer into the era when the first galaxies were forming. And what it has found, over and over, are galaxies and black holes that are bigger, brighter, and more mature than they should be for their age. Galaxies at redshifts where we expected to see dim proto-galaxies struggling to form their first stars. Black holes at epochs where we expected to see modest seeds just beginning to grow. TON 618 sits at a redshift of 2.219. That is not even that extreme anymore. Webb has found objects at redshifts of 10, 12, even 14. Objects seen as they were just a few 100 million years after the Big Bang. Some of those objects appear to harbor black holes weighing hundreds of millions or even billions of solar masses. If a black hole weighing 1 billion solar masses can exist 400 million years after the Big Bang, then the seed formation problem is even worse than TON 618 suggests. There is almost no time at all for conventional growth. The universe keeps handing us objects that should not exist, objects that are too big, too bright, too mature for their age, and every one of them is a message, a signal that our models are incomplete, that the assumptions we have been using to understand how black holes grow, how galaxies form, how the universe evolved from a hot, smooth fog into the structured cosmos we see today, those assumptions are missing something fundamental. TOR 618 is not an anomaly. It is the clearest, loudest, most undeniable example of a problem that runs deeper than one object. It is the flagship case, the one that forces the conversation, the one that sits in the data like a weight we cannot lift. 66 billion solar masses, 3 billion years after the Big Bang, already shining, already feeding, already impossible by the rules we thought we understood. And the question it demands is not just how did this happen? The question is what else are we getting wrong? Because if a black hole this massive can exist this early, then the story we have been telling about the infant universe, about how matter assembled, about how the first stars and galaxies and black holes formed, that story is not just incomplete, it is broken. The universe has rules, not the kind you can break by being clever or rebellious, not the kind you can bend with enough funding or optimism, hard rules. Physical laws that govern how matter behaves, how energy moves, how time passes, how gravity shapes space. These are not suggestions, they are the operating system of reality. And for the most part, everything in the cosmos obeys them. TON 618 does not in the sense that it is violating physics. Black holes do not break the laws of nature. They are consequences of those laws taken to their logical extreme. But TON 618 breaks something else. It breaks the models, the timelines, the growth curves that astronomers have spent decades building to explain how objects like this are supposed to form. It sits in the data like a glitch, like a line of code that compiled correctly but produces an output no one can explain. Let us be specific about where the models fracture, because this is not a vague hand-waving concern about things being surprisingly big. This is a precise technical problem with measurements, curves, and equations that stop working when you plug in the numbers for TON 618. Start with the black hole mass function. That is the statistical distribution that describes how many black holes exist at each mass range across the universe. Plot it on a graph. Put black hole mass on the horizontal axis. Put the number of black holes at each mass on the vertical axis. What you get is a curve that rises steeply at the low end, peaks somewhere in the middle, and then drops off sharply at the high end. The curve makes sense. Small black holes are common because they form from individual collapsing stars. Every massive star that goes supernova has a chance of leaving behind a stellar mass black hole. There are billions of massive stars per galaxy. Do the math and you get a lot of small black holes. Supermassive black holes, the kind that sit at galaxy centers and weigh millions to billions of solar masses, are rarer. One per galaxy maybe, The Milky Way has one. Most large galaxies have one. Small galaxies might not. So the number drops as you move up the mass scale. That is expected. That is what models predict. But the curve does not just drop, it plummets. The number of black holes falls off exponentially as you move toward the highest masses. By the time you get to 10 billion solar masses, the curve is almost touching the floor. Objects that heavy should be extraordinarily rare, so rare that finding even one requires surveying huge volumes of the universe. And then there is TON 618, 66 billion solar masses, sitting so far out on the tail of the distribution that it barely fits on the graph. Not just rare, anomalously rare, the kind of rare that makes statisticians nervous. One object by itself is not necessarily a problem. Rare things happen. The universe is big. Outliers exist. But TON 618 is not the only ultramassive black hole astronomers have found. There are others. Holmberg 15A, Phoenix A, IC 1101, a small but growing list of black holes that weigh tens of billions of solar masses. Each one pushes further out on the tail of the distribution. Each one makes the models less comfortable. The issue is not that these objects exist. The issue is that they exist in numbers higher than the mass function predicts. If the curve is accurate, ultramassive black holes should be so rare that you would need to survey the entire observable universe to find maybe one or two. Instead, we have found several within a relatively small sample of observed quasars. That suggests the tail of the distribution is not as steep as the models say it should be. Something about the physics of black hole growth at the highest masses is different from what we assumed. Which brings us to the growth problem. Again, because the mass function is not just a curve someone drew, it is the output of simulations, models that start with the conditions of the early universe and run forward through billions of years of cosmic history, tracking how black holes form, grow, merge, and evolve. Those simulations incorporate everything we know about star formation, gas dynamics, feedback from supernovae and quasars, galaxy mergers, dark matter halos, all of it. Run the simulations and they produce a mass function that matches observations beautifully, except at the very top, the tail, the ultramassive end. There, the models consistently underpredict the number of objects like TON 618, which means something in the simulations is wrong. Either the initial conditions are off, or the growth physics is incomplete, or there is a process we have not accounted for that operates specifically at the highest masses. One possibility is super-Eddington accretion. We talked about the Eddington limit in the last chapter, the theoretical speed limit on how fast a black hole can grow by eating gas. Radiation pressure from the infalling material pushes outward and eventually chokes off the inflow. That is the standard picture. But what if, under certain conditions, black holes can exceed that limit? The idea is not as crazy as it sounds. If the accretion flow is very dense and geometrically thick, radiation can get trapped inside the infalling gas instead of escaping. The photons scatter off electrons and atoms in the flow, losing energy and momentum before they can push outward effectively. In that scenario, the black hole can keep eating even as it radiates furiously because the radiation is not getting out fast enough to stop the inflow. The gas falls in faster than the light can escape to push it back. This is called photon trapping, and it has been studied in simulations. Under the right conditions, it can boost growth rates by factors of several or even 10 above the standard Eddington limit. If TON 618 went through even a few episodes of super-Eddington growth, each lasting a few tens of millions of years, that could significantly increase its final mass beyond what conventional accretion allows. The catch is that super-Eddington accretion is hard to sustain. It requires a continuous supply of very dense gas. Any interruption, any feedback from the black hole that disrupts the flow, and the process shuts down. You go back to normal Eddington limited growth or slower. So invoking super Eddington growth does not solve the problem by itself. It just shifts the question. Instead of asking how the black hole grew so fast, you are asking how it maintained the gas supply needed to sustain super Eddington growth for long enough to matter. Then there is spin. Black holes rotate. They have angular momentum. The spin rate affects how efficiently a black hole can convert infalling mass into radiation. A rapidly spinning black hole is more efficient. It can extract more energy from the accretion disk. More energy means more radiation. More radiation means more pressure pushing outward. More outward pressure means slower growth. This is counterintuitive. You would think a more efficient black hole would grow faster. But efficiency here means converting mass into light. A highly efficient black hole radiates away a larger fraction of the infalling mass as energy before that mass crosses the event horizon and adds to the black hole's weight. A less efficient black hole, one spinning slowly or not at all, radiates less and keeps more of the mass. So, paradoxically, slower spinning black holes can grow faster. If TAN 618 grew primarily through steady accretion, it probably could not have been spinning very fast for most of its life. High spin would have made the growth too slow. But black hole spin is not static, it evolves. Every time a black hole eats a clump of gas or merges with another black hole, the spin can change. If the infalling material is aligned with the black hole's rotation, the spin increases. If it is misaligned or counter-rotating, the spin decreases. So maybe TAN 618 grew through a combination of phases, periods of slow spin and rapid growth, periods of high spin and slower growth, mergers that reset the spin, chaotic inflows that averaged out the angular momentum. The exact history is impossible to reconstruct from 10 billion light-years away. But the fact that the black hole reached 66 billion solar masses at all suggests its spin evolution must have been favorable. It must have spent enough time in configurations that allowed rapid mass accumulation without being slowed down by excessive radiative efficiency. This is all speculation. We cannot measure the spin of TAN 618 directly. We can barely measure its mass. Spin is even harder. It requires high-resolution observations of the inner accretion disk, looking for relativistic effects like frame dragging that distort the spectrum in ways that depend on how fast the black hole is rotating. That kind of observation is difficult even for nearby supermassive black holes. For something as distant as TAN 618, it is currently impossible. So we are left inferring what the spin might have been based on what growth rate the models require. And the answer is that the spin must have been just right, not too high, not too low, Goldilocks spin, which is another way of saying we do not really know. Now connect this to the cosmic microwave background. The CMB is the faint glow of radiation left over from the early universe, about 380,000 years after the Big Bang. Before that point, the universe was too hot for atoms to form. It was a dense plasma of electrons and protons and photons all scattering off each other constantly. Light could not travel freely. The universe was opaque. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, the photons decoupled. They stopped scattering and started traveling in straight lines. Those photons have been flying through space ever since, stretched by the expansion of the universe from visible and ultraviolet wavelengths into microwaves. That is the CMB. A snapshot of the universe as it was 380,000 years after the Big Bang, frozen in light and stretched across the sky. The CMB is not perfectly uniform. It has tiny temperature fluctuations, hot spots and cold spots at the level of about 1 part in 100,000. Those fluctuations are not noise, they are the seeds of structure. Regions that were slightly denser than average, slightly more matter packed into a given volume. Gravity amplifies those density differences over time. Dense regions pull in more matter. They grow denser. Less dense regions lose matter. They grow emptier. Over millions and billions of years, the tiny fluctuations in the CMB grow into galaxies, galaxy clusters, and the large-scale structure of the universe. The properties of those fluctuations, their size, their amplitude, their statistical distribution, are encoded in the CMB. Telescopes like the Planck satellite have mapped the CMB with extraordinary precision. From those maps, cosmologists extract the initial conditions of the universe, how smooth or lumpy it was, how much dark matter and ordinary matter it contained, how fast it was expanding. All of that information is sitting in the CMB, waiting to be read. And here is where ton 618 becomes a problem. The black hole exists at a time when the universe was 3 billion years old. That is only 2.6 billion years after the CMB decoupled. In cosmic terms, that is not a lot of time. The structures visible in the CMB are tiny. Density fluctuations of 1 part in 100,000. To go from that level of smoothness to a black hole weighing 66 billion solar masses requires amplifying those fluctuations by an enormous factor. You need matter to collapse into halos, halos to merge into galaxies, galaxies to feed black holes to grow, all within 2.6 billion years. The standard models of structure formation, the ones based on the CMB measurements, predict that this process should take longer, not impossibly longer, not prohibitively longer, just longer. The timeline is tight. Tarshan 618 is right at the edge of what the models allow, maybe slightly over the edge, depending on whose models you trust. The fact that 2n618 exists at the mass it does, at the redshift it does, puts pressure on the initial conditions. Specifically, it suggests that the density fluctuations in the region where 2n618 formed must have been on the high end of the distribution, not impossibly high. The CMB allows for statistical variations. Some regions are denser than others. That is expected. But 2n618 had to form in a region that was not just dense. It had to be exceptionally dense. A rare peak in the density field, the kind of peak that shows up only occasionally when you survey large volumes of space. The more ultramassive black holes we find at high redshifts, the more those rare peaks we need, and if we find too many, the statistics start to break. You can only invoke so many rare events before rare stops being the right word. If ultramassive black holes are turning up in every deep survey, then either they are not as rare as the models predict, or the initial conditions in the early universe were lumpier than the CMB suggests. Neither option is comfortable. If ultramassive black holes are common, the growth models are wrong. If the early universe was lumpier than the CMB indicates, the cosmological models are wrong. Either way, something has to give. There is another angle. The existence of TON618 implies that the universe was capable of assembling very massive structures very quickly, not just the black hole itself, the entire environment around it. A galaxy massive enough to host a 66 billion solar mass black hole is not a small galaxy. It is a giant, probably an elliptical or a massive bulge-dominated system weighing hundreds of billions or even a trillion solar masses in stars and dark matter combined. Building a galaxy that massive in 3 billion years is hard. Not impossible, but hard. It requires a lot of mergers, a lot of gas inflow, a lot of star formation, all happening in rapid succession. And it has to happen in a way that funnels enough material toward the center to keep feeding the black hole without blowing all the gas out into intergalactic space. Feedback from star formation and the quasar itself should, in theory, regulate the process, slow it down, prevent runaway growth, but TON 618 grew anyway. The 2021 ALMA observations added another wrinkle. They revealed an enormous Lyman Alpha nebula surrounding TON 618, a cloud of glowing hydrogen gas stretching more than 100 kiloparsecs across. That is over 300,000 light-years. For reference, the Milky Way is about 100,000 light-years in diameter. This nebula is 3 times that size, and it is not just sitting there. It has structure. An inner molecular outflow, cold gas in the circumgalactic medium, each component weighing around 50 billion solar masses. That much gas sitting around a quasar is unusual. Normally, quasar feedback is supposed to blow gas away. The radiation pressure and winds from the accretion disk heat the surrounding gas and push it outward, shutting down star formation and eventually starving the quasar itself. That is the standard feedback loop. It is how quasars regulate their own growth and why they do not grow indefinitely. TON 618 has 50 billion solar masses of cold gas just sitting in its neighborhood. That suggests the feedback is not working the way models predict. Or it is working, but the gas supply is so enormous that even after the quasar blows away huge amounts of material, there is still plenty left over. Either way, it is more evidence that the environment around TON 618 is extreme, not just in terms of the black hole mass, in terms of the entire system. The galaxy, the gas, the star formation, the mergers, all of it operating at levels that push the boundaries of what models comfortably allow. Put all of this together, and what you get is not a single broken rule. It is a cascade, a series of assumptions and predictions that work beautifully for normal black holes and normal galaxies but start to crack when you apply them to TON 618. The mass function predicts fewer ultramassive black holes than we observe. The growth models require near-perfect conditions to reach 66 billion solar masses in the available time. The spin evolution has to be just right. The initial density fluctuations have to be on the high end. The gas supply has to be enormous and sustained. The feedback has to be weak enough not to shut down growth, but strong enough to produce the observed outflows. Every single one of those conditions is plausible. None of them violates physics, but requiring all of them to line up at once for a single object starts to feel less like an explanation and more like an excuse, like trying to justify a data point by invoking a series of coincidences. Science does not like coincidences. When you need everything to go right for your model to work, that is usually a sign that the model is incomplete, that there is a piece of the puzzle you have not found yet, a process you have not accounted for, a variable you have not measured. TON 618 is that sign. It is the object sitting in the data telling astronomers plainly that something about the current understanding of black hole growth, galaxy formation, and the early universe does not add up. The equations work, the physics is sound, but the timeline is too tight. The mass is too large. The conditions required are too specific. And the more we look, the more objects like TON 618 we find, each one adding weight to the case that the models are missing something. James Webb has made it impossible to ignore. For decades, TON 618 could be written off as an outlier, a statistical fluke, one weird object in a big universe. But Webb has been finding massive galaxies and massive black holes at redshifts where they should not exist, over and over, consistently. Objects that are too bright, too mature, too organized for their age, and every one of them is asking the same question Ton 618 asked first. How did the universe build things this big, this fast? And what does that mean for everything we thought we understood about how it all began? A new dawn, new mysteries. James Webb and the infant cosmos. The universe keeps getting stranger. That is the unavoidable conclusion from the last 2 years of observations. Not stranger in a vague poetic sense, stranger in a measurable, documented, peer-reviewed sense, stranger in a way that keeps forcing astrophysicists to stand up at conferences and say out loud that the models they have spent decades building might be fundamentally incomplete. And the tool delivering that uncomfortable news is a telescope that was not even supposed to launch, a telescope that sat in storage for years while Congress argued about funding, a telescope that was over budget, behind schedule, and at one point looked like it might never make it into space. A telescope that finally launched on Christmas Day 2021 unfolded itself one terrifying step at a time over the course of a month, and then started sending back images that immediately made every astronomy textbook feel outdated. The James Webb Space Telescope, JWST Webb. If you remember the first images released in July 2022, you remember the reaction, not just from scientists, from everyone. The deep field image, the galaxy cluster, the spectrum of an exoplanet atmosphere. Pictures so sharp and so detailed that they did not look like space photographs. They looked like concept art, like something a visual effects team had rendered for a science fiction film. Except they were real. Those were actual photons that had traveled billions of years across space, bounced off a gold-plated mirror sitting 1.5 million kilometers from Earth, and been captured by instruments sensitive enough to detect the heat signature of a bumblebee on the moon. The primary mirror is 6.5 meters across. That is more than 21 feet. For comparison, Hubble's mirror is 2.4 meters. Webb's mirror has roughly 6 times the light-gathering area. More importantly, Webb observes in the infrared. Hubble worked primarily in visible and ultraviolet light. That difference is everything when you are trying to look at the early universe. Light stretches as it travels through expanding space. The further away an object is, the more its light has been stretched by the time it reaches us. Ultraviolet light from a very distant galaxy gets stretched into visible light. Visible light gets stretched into infrared. If you want to see the first galaxies, the ones that formed a few 100 million years after the Big Bang, you need to look in the infrared. Hubble could see hints of those galaxies at the edge of its capability. Webb was designed specifically to see them clearly. And it has, over and over, with a clarity that has left astronomers scrambling to explain what they are looking at. The problem is not that Webb is finding early galaxies. Everyone expected that. The problem is what those galaxies look like. They are not small, they are not dim, they are not the faint, scattered proto-galaxies that models predicted. Some of them are massive, bright, organized, galaxies that look like they have already been through billions of years of evolution, sitting in an era when the universe itself was only a few 100 million years old. And many of them appear to harbor supermassive black holes that are already weighing hundreds of millions or even billions of solar masses. Black holes that, by every growth curve astronomers have drawn, should not have had time to grow that large yet. This is the Ton 618 problem all over again, except now it is not one object, it is dozens, maybe hundreds, depending on how the follow-up observations shake out. Webb is finding what some researchers have started calling impossibly early massive black holes. Objects at redshifts of 10, 12, even 14, redshifts that correspond to the universe being 300, 400, 500 million years old, epochs when the first stars were supposed to still be figuring out how to ignite. And there, sitting in the data, are black holes that weigh as much as 1 billion suns. Run the numbers and the timeline does not work. Start with a stellar mass black hole at 10 solar masses. Grow it at the Eddington limit. Double every 50 million years. At 500 million years after the Big Bang, you should have a black hole weighing maybe a few thousand solar masses, not a few 100 million, not a billion. The gap is enormous. Orders of magnitude. So either the black holes are not growing from stellar mass seeds, or they are growing much faster than the Eddington limit allows, or they started much larger than 10 solar masses. Those are the only options, and every one of them requires invoking physics or conditions that we have not directly observed. TAN 618 used to be the flagship example of this problem. A 66 billion solar mass black hole sitting at a redshift where it should not have had time to grow that large. For years, it was treated as an outlier, a statistical edge case. The universe is big, weird things happen. One ultra-massive black hole at high redshift might just be the result of everything going right in one rare corner of the cosmos. But Webb is showing that TAN 618 is not an outlier. It is part of a pattern that extends even further back in time. If you can grow a 66 billion solar mass black hole by the time the universe is 3 billion years old, and Webb is finding billion solar mass black holes when the universe is only a few 100 million years old, then the seed formation problem is not limited to ultramassive black holes. It applies across the board. Something about how black holes form and grow in the early universe is different from what the models predict. One of the ideas getting serious attention now is direct collapse. We talked about this earlier. The idea that under certain conditions, a massive cloud of gas in the early universe could collapse straight into a black hole without forming stars first, no stellar evolution, no supernova, just gas collapsing under its own gravity into a black hole weighing 100,000 or even 1 million solar masses right from the start. If that happened, you would bypass the entire slow growth phase. You would not need to double from 10 solar masses over and over again for hundreds of millions of years. You would start with a massive seed and grow from there. The timeline becomes much more manageable. A black hole starting at 1 million solar masses can reach 1 billion solar masses in a few 100 million years without requiring anything exotic, just steady Eddington limited accretion. The problem is proving that direct collapse actually happens. The conditions required are extreme. You need a very massive gas cloud. You need it to stay hot. You need intense ultraviolet radiation from nearby sources to prevent the gas from cooling and fragmenting into stars. Those conditions might have existed in the early universe, but we have never observed them directly. Direct collapse is a theoretical possibility, not a confirmed process. It works in simulations under the right assumptions. Whether nature actually does it is still an open question. Webb might be able to answer that question. If direct collapse black holes exist, they should have signatures, specific patterns in their spectra, specific ratios of heavy elements, specific relationships between the black hole mass and the surrounding galaxy. Webb has the sensitivity and resolution to look for those signatures. Over the next few years, as more data comes in and more high redshift black holes are analyzed in detail, astronomers will be able to test whether the direct collapse model actually explains what they are seeing, or whether something else is going on. Another idea that keeps surfacing is super-Eddington accretion. Maybe black holes in the early universe were not limited by the standard Eddington rate. Maybe the gas was so dense and the inflow so chaotic that radiation pressure could not effectively shut down the accretion. In that scenario, black holes could grow much faster than the standard models allow. Not forever. Super Eddington growth is hard to sustain, but even a few episodes lasting a few tens of millions of years could boost a black hole's mass significantly. Webb is finding clues that might support this. Some of the early massive black holes show signs of extremely active accretion, broad emission lines, high luminosities, outflows that suggest the black hole is feeding at a rate that pushes the boundaries of what standard accretion physics predicts. That does not prove super Eddington growth is happening, but it is consistent with it. And the more examples Webb finds, the harder it becomes to explain them all away as statistical flukes. Then there is the most speculative idea of all, primordial black holes. Primordial black holes are not remnants of dead stars. They are black holes that would have formed in the first fractions of a second after the Big Bang, before the first atoms, before the first particles even settled into stable forms. In the chaotic soup of the earliest moments, if density fluctuations were large enough in certain regions, those regions could have collapsed directly into black holes, tiny ones weighing less than a gram, massive ones weighing thousands of solar masses. A whole spectrum of masses, depending on the size and amplitude of the fluctuations. Primordial black holes have never been directly detected. They are a theoretical construct, a possibility allowed by physics but not required by any observation. Some physicists have proposed that primordial black holes could make up some or all of the dark matter in the universe. Others have proposed that they could serve as seeds for supermassive black holes. If primordial black holes exist, and some of them weighed thousands or even millions of solar masses, they would solve the seed problem instantly. You would not need to invoke direct collapse or super Eddington growth. You would just need those seeds to exist. The trouble is evidence, or the lack of it. Primordial black holes are hard to detect. If they are small, they do not emit much radiation. If they are large, they look like any other black hole, and there is no way to tell from a distance whether a given black hole formed from a collapsed star or from a density fluctuation in the early universe. The only way to distinguish them is by their mass distribution. If you find black holes with masses that do not fit the stellar remnant or supermassive categories, that might be a hint, but it is a weak hint. And so far, the observations have not provided compelling evidence one way or the other. Webb is not going to detect primordial black holes directly, but it might provide indirect evidence. If early massive black holes are common, and their masses do not fit what stellar collapse or direct collapse models predict, that would strengthen the case for an alternative formation mechanism. Primordial black holes would be one possibility, not the only one, but one that would have to be taken seriously. The broader point is that Webb is forcing the field to confront questions that used to be theoretical niceties. How do black hole seeds form? How fast can they grow? What are the initial conditions in the regions where the first supermassive black holes assembled? These questions have always mattered, but for a long time the data was too sparse to push them. Astronomers could propose models, run simulations, make predictions, and there were not enough observations of early black holes to definitively say which models were right and which were wrong. Now there are. Webb is delivering a flood of data. High redshift galaxies, high redshift black holes, spectra, luminosities, masses, more objects than anyone expected, and the pattern is consistent. The early universe was building massive structures faster than the standard models predict, not just black holes, galaxies too. Some of the galaxies Webb has found at high redshift are so massive and so well organized that they push right up against the limits of what the cosmological models allow. To form a galaxy weighing hundreds of billions of solar masses in a few 100 million years requires nearly perfect efficiency. Almost every available atom of gas has to turn into stars. In the real universe, efficiency is nowhere near that high. Most gas never forms stars. It gets heated, blown out, or just sits around doing nothing. But these early galaxies appear to have done it anyway, which means something about the early universe was different. Maybe the gas was denser, maybe the star formation rate was higher, maybe feedback from supernovae and quasars was less effective at shutting down growth. Maybe dark matter halos in the early universe were more efficient at funneling gas inward. Whatever the explanation, the data is clear. The infant cosmos was more active, more efficient, more productive than models predicted, and TOEN 618 fits right into that picture. It is not an anomaly anymore, it is an example. One of the clearest, largest, most extreme examples of a phenomenon that Webb is now showing was widespread, massive black holes growing faster than they should. Massive galaxies assembling sooner than they should. An early universe that looks less like a slow, tentative warm-up and more like an explosion of structure formation happening all at once. This has implications beyond black holes. If the early universe was building massive structures faster than models predict, that means the initial conditions had to be different. The density fluctuations had to be larger, or the dark matter had to behave differently, or the physics of gas cooling and star formation had to operate under different rules. Any of those changes ripple forward through the entire history of the cosmos. They affect when galaxies formed, when stars formed, when planets formed, when the conditions for life became possible. TOEN 618 used to be a curiosity, a strange object at the edge of the data, something to write papers about and then move on. Webb has turned it into a signpost, a marker pointing at a deeper problem. The universe in its first few 100 million years was not behaving the way cosmologists thought it would. It was building faster, growing larger, assembling structures with an efficiency that does not fit the models. And the more Webb looks, the more examples it finds. Every deep field observation, every spectroscopic survey, every follow-up on a candidate high redshift galaxy, more massive black holes, more organized galaxies, more objects that should not exist yet but do. This is not a crisis in the sense that physics is broken. The laws of gravity still work, stars still fuse hydrogen, black holes still trap light. But the timeline is broken. The growth curves are broken. The models that were supposed to describe how the universe went from a smooth, hot fog to the structured cosmos we see today are not matching the observations. And when models do not match observations, the models have to change. That process is happening right now. Papers are being published every month revising the estimates for how fast black holes can grow, how massive the seeds could have been, how efficient early star formation might have been. Conferences are being held where researchers argue over whether direct collapse is common or rare, whether super-Eddington accretion is sustainable, whether primordial black holes need to be invoked at all. The field is in flux. Not because anyone made a mistake, but because the data is pushing into territory that the old models did not anticipate. And at the center of that conversation, like a weight that refuses to move, sits TOEN 618, 66 billion solar masses, 10.8 billion light-years away, shining so brightly that we could see it with a telescope in Mexico in 1957. A black hole that should not have had time to grow that large, sitting in an era when the universe should not have been capable of building something that massive. Webb has shown that TOEN 618 is not alone. It is part of a population of massive black holes at high redshifts that the models consistently underpredict. And every new observation, every new spectrum, every new mass estimate adds weight to the conclusion that something fundamental about the early universe is not captured in the current framework. The question is no longer whether black holes like TON 618 can exist. They do. The question is how. And the answer, whatever it turns out to be, is going to require rethinking some of the most basic assumptions about how the cosmos assembled itself in the first billion years after the Big Bang. Webb will keep looking. It has years of observations ahead of it. More deep fields, more high redshift surveys, more spectra of distant quasars and galaxies. Each observation will add another piece to the puzzle, another constraint on the models, another hint at what the early universe was actually doing while it was supposed to be slowly warming up. And in the meantime, TON 618 will keep shining. The light that left it 10.8 billion years ago is still arriving, still hitting detectors, still being analyzed, still asking the same question it asked the first time someone looked closely at that faint blue smudge on a photographic plate. How did this happen? How does a universe barely out of its infancy produce something this extreme? And what does that mean for everything else we think we know? The answers are coming, slowly, one observation at a time, one revised model at a time. One uncomfortable conference presentation at a time. Webb is delivering the data, the field is doing the work. And TON 618, the largest black hole ever found, the object that broke the models before anyone realized the models could break, is finally getting the context it deserves. It is not a freak, it is a clue. A signal from the early universe telling us plainly that the story we thought we understood is incomplete, that there are processes, conditions, mechanisms operating in the infant cosmos that we have not accounted for, that the timeline is tighter, the growth is faster, the structures are larger than we predicted, and if we got that wrong, what else did we miss? What other assumptions are sitting quietly in the models, unchallenged, waiting for the next round of observations to prove them incomplete? What other objects are out there, too far or too faint for current telescopes, that will one day show up in a survey and force another round of revisions? The universe is not obligated to make sense to us. It does not care whether our models are elegant or our timelines are comfortable. It just is. And our job, the only job science has ever had, is to look at what is actually there and build explanations that fit the data, not the other way around. TON 618 is what is actually there, a 66 billion solar mass black hole in the early universe, and Webb is showing us that it is not alone, that the early cosmos was stranger, faster, more extreme than we thought, that the rules we wrote down were incomplete, that the story is bigger than we realized, and somewhere in that bigger story, in the data still arriving, in the observations still being planned, in the models still being revised, is the answer. The explanation for how a universe barely 3 billion years old managed to produce a black hole weighing as much as 66 billion suns. We do not have that answer yet, but for the first time, we are asking the right questions, and we have the tools to find out. Is it coming for us? Fact vs. fiction of cosmic threats. There is a question sitting in the back of your mind right now. You might not have said it out loud, you might not have fully formed it into words, but it is there, a quiet, anxious whisper that started the moment you saw the title of this video, the moment you heard the number 66 billion solar masses, the moment you realized we were talking about the largest black hole ever found. The question is simple: is it coming for us? That is the thing about black holes. They carry a weight in the popular imagination that goes beyond their actual physics. They are cosmic horror made real, monsters that devour everything, holes in space that nothing can escape. And when you describe one that weighs 66 billion times more than our sun, sitting out there in the dark, the instinctive reaction is fear. not abstract philosophical concern about cosmological models. Fear, the kind that asks whether you should be worried, whether this thing, this impossibly massive object shining at us from across the universe, poses any kind of threat. The answer is no, but the reasons why are more interesting than the answer itself. And the truth about what Ton 618 actually means for Earth is stranger than any threat it could pose. Let us start with the basics. Where is Ton 618? Not in some vague sense. Specifically, what direction is it? How far away is it? And is that distance changing? Ton 618 sits near the border of two constellations, Cants Venatici, the hunting dogs, and Coma Berenices, Berenice's hare. If you go outside on a clear night in the northern hemisphere during spring and look toward the area between the handle of the Big Dipper and the bright star Arcturus, you are looking in roughly the right direction. Not that you would see anything. Ton 618 is far too faint to spot with the naked eye or even a backyard telescope, but that is the patch of sky where it sits, not moving, not drifting across the constellations, just sitting there, exactly where it has been since long before anyone was around to notice. Now for the distance. This is where things get strange, because there are two answers, and both of them are correct, and neither of them means what you probably think it means. The first distance is light travel time. The light we see from Ton 618 today has been traveling toward Earth for about 10.8 billion years. That photon, the one that left the accretion disk around Ton 618 and eventually hit a detector in one of our telescopes, spent 10.8 billion years crossing space. That is 3/4 of the current age of the universe. That photon began its journey when the cosmos was less than 1/4 of its present age. Earth did not exist. The Sun did not exist. The Milky Way was still assembling itself from smaller galaxies merging together in a chaotic dance of gravity and gas. So in one very real sense, Ton 618 is 10.8 billion light-years away. That is the distance the light traveled. That is how far back in time we are looking when we observe it. But that is not where Ton 618 is now. The second distance is the co-moving distance. That is the actual physical separation between Ton 618 and Earth at this moment, accounting for the fact that space itself has been expanding the entire time that photon was in transit. The co-moving distance to Ton 618 is about 18.2 billion light-years. 18.2 billion, not 10.8. The gap between those two numbers is not a mistake. It is not a rounding error. It is the signature of cosmic expansion. The universe has been stretching the entire time that light was traveling. The space between Ton 618 and Earth was growing while the photon was crossing it. So even though the photon only traveled for 10.8 billion years, the distance it covered in terms of how much space now separates the two endpoints is much larger. Think of it like this. Imagine you are walking across a long elastic mat. You start at one end. Your friend is standing at the other end, 18 feet away. You start walking toward them at a steady pace, 1 foot per second. But while you are walking, the mat is stretching. Your friend is not moving. You are not moving relative to the mat under your feet. But the mat itself is getting longer. So even though you walk at 1 foot per second for 18 seconds, by the time you reach your friend, the mat is no longer 18 feet long. It is 30 feet long. You traveled 18 feet in your own reference frame, but the separation distance between where you started and where you ended is larger because the mat stretched while you were moving. That is what happened to the light from Ton 618. It traveled for 10.8 billion years at the speed of light, but the space it was traveling through was expanding the entire time. So by the time it reached Earth, the total separation distance had grown to 18.2 billion light-years. Here is the important part. That expansion is still happening, right now, as you are reading this. The space between Earth and TOM 618 is getting larger. Not because TOM 618 is flying away from us through space, because space itself is expanding. The universe is not a static backdrop. It is a dynamic structure that has been growing since the Big Bang and continues to grow today. Which means TOM 618 is not coming toward us. It is receding. Every second, the comoving distance between that black hole and this planet increases. Not dramatically, not at relativistic speeds, but measurably. The universe's expansion is carrying TOM 618 away from us, and there is no force capable of reversing that. Gravity does not reach across 18 billion light-years and pull things together. That is not how gravity works at cosmological scales. Gravity is strong locally. It holds you to the ground. It keeps the moon orbiting Earth. It keeps the planets orbiting the sun. It binds stars into galaxies and galaxies into clusters. But beyond a certain scale, gravity loses. Expansion wins. The space between galaxy clusters is growing, and nothing those clusters do gravitationally can stop it. TOM 618 sits in a region of space that is part of the observable universe but not part of what physicists call our gravitational neighborhood. The black hole's gravity is immense on the scale of its own galaxy. It shapes the orbits of billions of stars. It pulls in gas from hundreds of thousands of light-years away. It powers a quasar bright enough to be seen across most of the cosmos, but at a distance of 18 billion light-years, its gravitational effect on the solar system is zero, not small, not negligible, zero. You are in more gravitational danger from the moon than you are from TOM 618. You are in more gravitational danger from Jupiter. From the Sun, obviously. From the supermassive black hole at the center of the Milky Way, which sits only 26,000 light-years away and weighs 4 million solar masses. That black hole, Sagittarius A star, is 16,000 times closer than TOM 618 and 6,600 times less massive. And even Sagittarius A star poses no threat to Earth. Its gravity does not reach this far out in any meaningful way. We orbit the galactic center at a safe distance, moving at about 220 kilometers per second in a slow, lazy orbit that takes about 230 million years to complete. The black hole at the center is not pulling us in. It is just sitting there, doing what supermassive black holes do, holding the galaxy together gravitationally while the rest of us go about our business. If the black hole at the center of our own galaxy, a black hole we share a galaxy with, does not threaten us, then a black hole 18 billion light-years away certainly does not. So no. TOM 618 is not coming for us. It is not headed this way. It is not going to swallow the Earth or the solar system or the Milky Way. It is not a threat in any physical sense. The photons arriving from it are the only thing from TOM 618 that will ever reach us. And photons do not carry mass. They do not exert gravity. They are just light, information. A signal from a distant corner of the universe telling us that something extremely massive existed 10.8 billion years ago. But here is where the truth gets stranger than the fiction. Because while TOM 618 is not a physical threat, its existence is unsettling in a different way, not because it is dangerous, because it should not exist. The fact that a black hole weighing 66 billion solar masses can form in the time available, in the conditions present in the early universe, forces us to question fundamental assumptions about how structure formation works. Every model of galaxy evolution, every simulation of black hole growth, every timeline we have drawn for how the cosmos assembled itself from a smooth, hot fog into the rich, structured universe we see today, all of that is built on assumptions that TON 618 violates, not by breaking physics. Physics does not care what we assume, by existing at all, by sitting in the data as a fact that refuses to fit. The threat TON 618 poses is not to Earth. It is to our models, to our understanding, to the neat, clean, well-tested frameworks that cosmologists have spent decades building to explain how galaxies form, how black holes grow, how the universe went from the Big Bang to now. TON 618 is a crack in that framework, a weight sitting on a structure that was supposed to be able to hold it but is starting to show strain. And it is not alone. James Webb is finding more massive black holes at high redshifts, more galaxies that assembled faster than they should have, more objects that push right up against the limits of what the models allow. TON 618 used to be an outlier. Now it is part of a pattern, and patterns demand explanations. The most unsettling possibility is that the early universe was capable of things we have not accounted for, processes we have not observed, conditions we have not modeled. Maybe black holes can grow faster than the Eddington limit under certain circumstances. Maybe massive seeds formed through direct collapse or primordial fluctuations. Maybe the gas in the early universe was denser, hotter, more efficiently funneled into black holes than we assumed. Maybe feedback mechanisms that regulate black hole growth in the modern universe did not work the same way in the infant cosmos. Any of those possibilities would require revising the models, not just tweaking a parameter, revising, adding new physics, changing assumptions that have been treated as solid for decades. That is uncomfortable. Science does not like tearing down frameworks that work. But when the observations do not fit, the frameworks have to change. That is the rule. Data wins. Models adapt. So the real question is not whether TON 618 is coming for us. The real question is, what does its existence tell us about the universe we live in? What does it mean that objects this massive can form this early? What does that imply about the conditions in the first billion years after the Big Bang? And what else are we getting wrong? There is another angle here, the long-term future. Not of Earth, of TON 618 itself. Right now, TON 618 is an active quasar. It is feeding. Gas is spiraling into the accretion disk. Matter is being converted into radiation. The black hole is shining so brightly that we can see it across more than 10 billion light-years of space. But that phase does not last forever. Quasars are a stage in a galaxy's life, a phase when the central black hole has access to a large supply of gas and is feeding actively. Eventually, the gas runs out, or gets blown away by the quasar's own radiation, or star formation in the galaxy uses it up before the black hole can eat it. And when that happens, the quasar shuts off. The black hole does not disappear, it just goes dark. It stops feeding. The accretion disk fades. The radiation drops. What was once one of the brightest objects in the universe becomes invisible. A massive dark object sitting quietly at the center of a galaxy, waiting for the next inflow of gas to reignite it. Most supermassive black holes in the modern universe are in this quiescent state. Our own Milky Way's black hole is not actively feeding. It is just sitting there. Occasionally something drifts too close and gets eaten, producing a brief flare of radiation. But most of the time, Sagittarius A star is dark, quiet, a 4 million solar mass object doing nothing in particular. TON 618 will eventually enter that state. The light we see from it is 10.8 billion years old. The object we're observing existed when the universe was 3 billion years old. Today, at this moment, 13.8 billion years after the Big Bang, TON 618 is not shining the way we see it. The quasar phase ended long ago. The black hole is still there. It has probably grown even larger over the intervening billions of years, but the bright, active feeding phase we observe in our telescopes is ancient history. What TON 618 looks like now, we will not know for another 7 billion years. That is how long it will take for light from its present state to reach Earth. And in the far future, TON 618's fate is isolation. The universe's expansion is accelerating. Dark energy, whatever it is pushing space apart faster over time. Galaxies that are not gravitationally bound to each other are drifting apart. Galaxy clusters are becoming more isolated. In a few 100 billion years, the only galaxies we will be able to see from the Milky Way, assuming anyone is still around to look, will be the galaxies in our local group. Everything else will have receded beyond the cosmic horizon. The space between us and them will be expanding faster than light can cross it. Those galaxies will not be visible, not because they stopped existing, because the light they emit will never reach us. The universe will have stretched too far. TON 618 is not in our local group. It is not even in our local supercluster. It sits in a completely different region of space, billions of light years away. As the universe continues to expand and accelerate, the comoving distance between TON 618 and Earth will grow. Eventually, it will grow so large that no signal from TON 618, no light, no radiation, no information of any kind will ever be able to reach the Milky Way again. The black hole will still exist. It will still be sitting there, 66 billion solar masses or more, holding its galaxy together gravitationally. But from our perspective, it will have vanished, not destroyed, just unreachable, lost beyond the edge of the observable universe. That is the ultimate fate of most objects in the cosmos, not destruction, isolation. The universe will keep expanding, and the vast majority of galaxies will drift out of contact with each other. In the unimaginably distant future, trillions of years from now, galaxies will be alone, each one an island in a sea of empty expanding space. Black holes will still exist. Stars will have long since burned out. Planets will be cold and dead, but the black holes will remain, slowly evaporating through Hawking radiation over timescales so long that the current age of the universe is a rounding error by comparison. TON 618 will be one of those black holes, sitting in the dark, isolated, unreachable, slowly radiating away its mass one quantum fluctuation at a time until, in the incomprehensibly distant future, it finally evaporates completely and leaves nothing behind but a faint whisper of radiation dispersed across an empty universe. That is the fate of the largest black hole ever found. Not conquest, not expansion, not swallowing galaxies, just time, just entropy, just the slow, inevitable march toward equilibrium that governs everything in the cosmos. So is TON 618 coming for us? No, it is receding. It has always been receding. It will continue to recede until it vanishes beyond the horizon of what we can ever observe. The expansion of the universe guarantees that. The object we see when we point our telescopes at that patch of sky between Canes Venatici and Coma Berenices is not approaching. It is a memory, a signal from the past, a message written in light that has been traveling toward us for longer than Earth has existed, arriving just in time to tell us that the early universe was stranger, faster, more extreme than we thought. The real threat is not physical, it is intellectual. TON 618 threatens our models. It forces uncomfortable questions. It sits in the data like a weight that refuses to move, demanding explanations that do not yet exist. And the more we look, the more objects like it we find, the louder that demand becomes. James Webb is showing us that the infant cosmos was capable of building things that should not have had time to grow. That black holes like TOEN 618 are not flukes. That the assumptions we built our cosmological models on are incomplete. That the timeline is tighter, the growth is faster, the structures are larger than we predicted, and if we got that wrong, what else did we miss? That is the message TOEN 618 is sending, not a warning about physical danger, a signal that our understanding is incomplete. That the universe is bigger, stranger, more extreme than the frameworks we have built to describe it. That there are processes operating in the early cosmos that we have not accounted for. That the story we thought we understood is missing chapters, and the only way to find those chapters is to keep looking, keep observing, keep questioning, keep revising the models when they do not fit the data. Because the universe does not care whether our explanations are elegant. It does not care whether our timelines are comfortable. It just is. And our job is to look at what is actually there and build frameworks that fit. TOEN 618 is what is actually there. A 66 billion solar mass black hole in the early universe, receding, isolated, unreachable, and shining across more than 10 billion light-years of space to tell us that the cosmos is not done surprising us. The universe is warning, our evolving understanding. The universe does not owe us comprehension. That might be the single most important lesson TOEN 618 has to teach. Not a lesson about black holes or accretion rates or cosmological timelines. A lesson about us. About what it means to be a species barely a few 100,000 years old, standing on a rock orbiting an average star in an unremarkable galaxy, pointing instruments at the sky and expecting the cosmos to make sense. TOEN 618 does not make sense, not in the framework we built, not according to the models we trusted, not within the timelines we calculated. It exists anyway. 66 billion solar masses sitting in an era when our best physics says it should not have had time to grow that large. And the universe did not check with us first. It did not ask permission. It did not wait for our equations to catch up. This is the warning, not a threat, a reminder. The cosmos is under no obligation to behave according to human expectations. Our models are tools, useful tools. Tools that have explained an extraordinary amount about how reality operates. But they are not reality itself. They are maps. And TOEN 618 is the place where the map stops matching the territory. When that happens, when you find an object that breaks your model, you have two choices. You can dismiss it as an outlier, a statistical fluke, one weird data point in a big universe, or you can take it seriously. You can treat it as a signal, a message from nature telling you plainly that something in your framework is incomplete. For decades, astronomers chose the first option. TOEN 618 was catalogued, measured, studied, and then quietly filed away as an extreme case. The largest black hole ever found. Fascinating, certainly. Worth a few papers, but not a crisis. Not a reason to rethink fundamental assumptions about how black holes grow or how the early universe assembled itself. It was just sitting out there at the edge of the data, too far away and too unusual to force uncomfortable questions. James Webb changed that. Not by finding TOEN 618. That black hole was already known. Webb changed it by finding more. More massive black holes at high redshifts. More galaxies that assembled faster than models predicted. More objects that should not exist yet but do. Over and over, consistently. A pattern too strong to ignore, and when the pattern became undeniable, the field had to stop treating these objects as outliers and start treating them as evidence. Evidence that the models are wrong, not completely wrong, not broken beyond repair, but incomplete, missing something. And the only way forward is to figure out what that something is. This is how science actually works. Not the sanitized version taught in textbooks where theories emerge fully formed and experiments confirm them in neat linear progressions, the messy version. The one where models are built on assumptions that seem reasonable at the time, tested against observations that mostly fit, and then declared successful until something shows up that does not fit, and then the real work begins. The work of figuring out which assumptions were too strong, which simplifications went too far, which pieces of physics were left out because no one thought they mattered. Ton 618 matters. It matters because it sits at the intersection of multiple assumptions that are now under strain. The assumption that black holes grow primarily through steady accretion at rates governed by the Eddington limit. The assumption that supermassive black holes form from stellar mass seeds that start small and double slowly over hundreds of millions of years. The assumption that the early universe was inefficient at building massive structures. The assumption that feedback mechanisms regulate black hole growth by blowing away the gas supply before things get out of hand. Every one of those assumptions works beautifully for most black holes. For Sagittarius A star at the center of the Milky Way, for the black hole at the center of M87, for the population of supermassive black holes that astronomers have catalogued across the universe, but 2N 618 does not fit. And the more we look, the more objects like it we find, which means the assumptions are not universal. They work under certain conditions. And in the early universe, those conditions were different. Figuring out how they were different is the puzzle. And solving it requires more than just tweaking a parameter in a simulation. It requires rethinking what the first few billion years of cosmic history actually looked like, whether the gas was denser, whether star formation was more efficient, whether black hole seeds formed through processes we have never observed, whether accretion happened at rates faster than standard physics allows, whether mergers were more common, whether primordial black holes seeded the growth of supermassive ones, whether some combination of all of the above conspired to build objects that the modern universe could never replicate. The uncomfortable truth is that we do not know, not yet. The data is still coming in. Webb has only been operational for a few years. The surveys are still incomplete. The follow-up observations are still being scheduled. The theoretical models are still being revised. This is science in progress, not science as a finished product delivered in a textbook. Science as it actually happens, uncertain, iterative, full of competing ideas and arguments and papers that contradict each other because no one has figured out the right answer yet. And that is fine. That is how it is supposed to work. The discomfort is not a failure, it is a feature. It means the field is being forced to grow, to expand beyond the boundaries of what was previously understood, to incorporate new observations that do not fit the old frameworks, to build better models, not because the old ones were stupid or lazy or wrong in some fundamental sense, but because they were incomplete. And the only way to find the missing pieces is to keep looking at the things that do not fit and asking why. Ton 618 is one of those things. The clearest example, the most extreme case, the object that sits in the data like a weight no one can lift. And every attempt to explain it away, every model adjustment, every revised assumption adds another piece to the larger picture of what the early universe was actually capable of. There is a broader point here, one that goes beyond black holes and cosmology. The universe is full of objects we have not found yet, phenomena we have not observed, processes we have not imagined. The observable universe contains an estimated 2 trillion galaxies, 2 trillion. Each one with hundreds of billions of stars, each one potentially harboring a supermassive black hole at its center. and we have catalogued a tiny fraction of them. The deep field images from Hubble and Webb cover areas of the sky smaller than a grain of sand held at arm's length. What we have seen is a sample, a glimpse, a narrow keyhole view of a cosmos so vast that the numbers stop meaning anything. In that context, finding objects like TON 618 is not surprising. It is inevitable. The universe is big enough and old enough and strange enough that rare things happen, things that push the boundaries of what models predict, things that force revisions, things that remind us that nature does not care about our categories or our comfort levels. It just does what the laws of physics allow. And if those laws permit a black hole to grow to 66 billion solar masses in 3 billion years under the right conditions, then that is what happens, whether we predicted it or not. This is humbling, and it should be. Humility is not a weakness in science. It is a prerequisite. The moment you stop being surprised by what the universe shows you, the moment you start assuming your models are complete and your understanding is sufficient, that is the moment you stop being a scientist, because the job is never finished. There is always another observation, another anomaly, another object at the edge of the data that does not fit. And the only appropriate response is curiosity, not defensiveness, not dismissal. Curiosity, the drive to figure out what you missed. TON 618 is a gift in that sense. It is an object so extreme that it cannot be ignored, so massive that it cannot be explained away as a rounding error or a measurement mistake, so well documented that dismissing it is not an option. It forces the conversation. It makes cosmologists stand up at conferences and admit that the models are incomplete, that the timeline does not work, that something fundamental about black hole growth in the early universe is not captured in the current framework, and that admission, uncomfortable as it is progress, because you cannot fix a problem you refuse to acknowledge. The search for a unified explanation is ongoing. Some researchers are focusing on direct collapse, the idea that massive gas clouds in the early universe collapsed straight into black holes without forming stars first. Others are focusing on super-Eddington accretion, the possibility that black holes can grow faster than standard models allow under certain dense chaotic conditions. Others are looking at primordial black holes, the notion that seeds formed in the first moments after the Big Bang and gave supermassive black holes a massive head start. And still others are focusing on mergers. The idea that the early universe was so crowded and collision-rich that black holes grew primarily by combining with each other rather than by eating gas. Each of those ideas has strengths, each has weaknesses. And the answer, when it finally emerges, will probably involve some combination of all of them, because the universe does not care about clean explanations. It does not care whether one mechanism is sufficient or whether we need to invoke multiple processes. It just cares about what actually happened, and what actually happened in the first few billion years after the Big Bang was complex, chaotic, full of conditions that no longer exist, and processes that we have never directly observed. Reconstructing that history from observations of distant quasars and high redshift galaxies is like trying to piece together a crime scene from a handful of blurry photographs taken decades after the fact. You can make progress, you can narrow down the possibilities, but certainty is elusive, and maybe that is okay. Maybe the point is not to reach a final answer, but to keep asking better questions, to keep refining the models, to keep pushing the observations further and deeper, to keep building instruments that can see things no previous generation could see. Webb is extraordinary, the most powerful telescope ever launched, but it is not the last telescope. There will be others, larger mirrors, better detectors, new wavelengths, new techniques. Each one will extend the reach a little further. Each one will find objects that push the models a little harder, and each one will force the field to grow. TON 618 will not be the most extreme object forever. Something larger will eventually be found. Some black hole weighing 100 billion solar masses or more, sitting at an even higher redshift, breaking even more assumptions. And when that happens, the same process will repeat, the same discomfort, the same scramble to revise the models, the same arguments at conferences about which assumptions were too strong and which processes were left out. And that is fine. That is the nature of the work. Science does not end. It iterates, it improves, it builds on what came before and incorporates what comes next. And the objects that break the models are not obstacles. They are guideposts. Signals pointing toward the places where understanding is incomplete and growth is possible. There is a philosophical dimension here that is worth sitting with. Human beings have been looking at the sky for as long as we have been human. Tens of thousands of years, maybe hundreds of thousands, long before writing, long before cities, long before anything resembling modern science. We looked up and saw lights moving against the darkness, and we invented stories to explain them. Gods and heroes and monsters, myths that made the chaos feel ordered. That gave the lights meaning. Science is not so different. We still look up. We still see lights. We still invent stories to explain them. The difference is that our stories are testable. They make predictions. They can be proven wrong. And when they are proven wrong, we revise them. That process, that willingness to update the story when the data demands it, is what separates science from mythology. Not the stories themselves, the process. TON 618 is a light, a point in the sky, a signal from an object so far away and so ancient that the light reaching us today left that object before Earth existed. And the story we have been telling about that light, about how black holes grow and when they form and how massive they can become, is being revised, not because anyone made a mistake, but because the universe handed us new information. And the only responsible thing to do with new information is incorporate it. That is the warning TON 618 delivers, not a warning about danger, a warning about certainty. The universe is bigger than our models, stranger than our assumptions, more extreme than our predictions. And the moment we forget that, the moment we start treating our frameworks as complete, is the moment we stop learning. Because there is always another TON 618 waiting, another object at the edge of the data that refuses to fit. Another signal from the cosmos reminding us that reality does not care what we think is reasonable. Humanity's place in all of this is small, not insignificant, small. We are a young species on a young planet, orbiting a middle-aged star in a galaxy that is one of trillions. We have been doing science in any recognizable form for maybe 400 years. We have been observing the universe with telescopes for 4 centuries. We have been able to detect objects like TON 618 for less than 1 human lifetime. And in that brief flicker of time, we have learnt an extraordinary amount. We have measured the age of the universe. We have mapped its large-scale structure. We have identified the processes that build galaxies and stars and planets. We have begun to understand black holes, dark matter, dark energy, the cosmic microwave background, the expansion of space itself. That is remarkable, but it is not complete, and mistaking progress for completion is a trap. The map is not the territory, the models are not reality, they are tools, useful tools, tools that have taken us further than any previous generation could have imagined, but they are provisional, always provisional, always subject to revision when new data comes in, and new data is always coming in. TON 618 came in, and it broke things. Not catastrophically, not in a way that invalidates everything we know, but enough to force revisions, enough to make cosmologists uncomfortable, enough to start conversations about what the early universe was really like and how black holes really grow, and whether the assumptions we built our models on are as solid as we thought. Those conversations are happening right now, in journals, at conferences, in emails between collaborators scattered across the planet. Scientists arguing over data, running simulations, proposing new mechanisms, testing predictions. Some ideas will turn out to be wrong, some will turn out to be pieces of a larger answer, and the process will continue, because that is what science does. It does not stop at discomfort. It works through it, and somewhere in that process, in the iterative cycle of observation and theory and revision, is the explanation for TON 618, the answer to how a black hole that massive formed that early, the missing piece of physics that makes the timeline work. The process we have not observed yet, but that nature employed billions of years ago to build something so extreme that it still defies explanation more than a decade after its mass was first calculated. We will find that answer. Maybe not today, maybe not this decade, but eventually, because the tools keep getting better, the observations keep getting sharper, the models keep getting refined, and every new piece of data, every new high redshift black hole, every new massive galaxy in the infant universe, narrows the possibilities, eliminates the ideas that do not work, points toward the ideas that do. That is the trajectory, not certainty, progress, slow, iterative, sometimes frustrating progress toward a more complete understanding of how the cosmos operates. And TON 618 is part of that trajectory, not as an obstacle, as a catalyst, an object so extreme that it forces the field to grow, to question assumptions, to build better frameworks, to incorporate observations that do not fit the old models and use them to construct new ones that do. The universe is not done surprising us. It will never be done. Every time we build a more powerful telescope, we find things that were not supposed to be there. Every time we extend our reach, we encounter objects that break the rules we thought were solid. And every time that happens, the appropriate response is not frustration, it is excitement. Because those objects are the ones that teach us the most. They are the places where understanding grows, where models get tested and revised, where science does what it does best, which is change its mind when the data demands it. TON 618 demanded it, and the field is responding, slowly, carefully, with the rigor that good science requires. But responding, building new models, testing new ideas, searching for the missing pieces that will make the picture complete, or at least more complete than it was before. Because completion is not the goal, understanding is, and understanding is a process, not a destination. We are in the middle of that process, not at the beginning, not at the end, somewhere in the uncomfortable middle where the old models do not quite work and the new ones are not quite ready, where the observations are piling up faster than the theory can explain them, where every deep field image from Webb adds more objects to the list of things that should not exist yet but do. That is where cosmology is right now, and that is where it should be. Because science that is comfortable is science that is not being tested. And science that is not being tested is not really science, it is dogma. TON 618 is the test, the weight sitting on the scales, the object that refuses to fit. And the fact that it exists, that it shines at us from across more than 10 billion years of cosmic history, that its light carries a message saying plainly that the early universe was stranger and faster and more extreme than we predicted, that is not a failure of science. It is science working exactly as it should, finding the places where understanding is incomplete, identifying the gaps, and then doing the hard work of filling them in. That work is not finished. It will never be finished, because the universe is infinite in its capacity to surprise us, and our capacity to understand it, while extraordinary, is not infinite. It is growing, slowly, incrementally, one observation at a time, one revised model at a time, one uncomfortable conference presentation at a time, and that is enough. Because the alternative, the version where we stop looking and declare the models complete, is not science, it is surrender. TON 618 will not let us surrender. It sits in the data like a monument, a signal from the early universe, a message written in light that has been traveling toward us for longer than Earth has existed. And the message is clear. The cosmos is bigger than your models, stranger than your assumptions, more extreme than your predictions. And if you want to understand it, if you want to map the territory instead of just polishing the map, then you have to be willing to be wrong, to revise, to grow, to let the data lead instead of forcing it to fit. That is the warning, not a threat, a gift. The universe handing us an object so extreme that we cannot ignore it, so massive that we cannot explain it away, so well documented that dismissing it is not an option, and in doing so forcing us to do what scientists are supposed to do, which is look at what does not fit and ask why, and then build better frameworks, better models, better understanding. Not because the old ones were failures, but because the universe is not done teaching us. And the only way to learn is to pay attention when it speaks. TON 618 is speaking, loudly, clearly, across more than 10 billion years of space and time, and the message it carries is one that every scientist, every human being who has ever looked at the sky and wondered what is out there should take to heart. The cosmos does not owe us comprehension, but it offers it, in pieces, in signals, in objects at the edge of the data that do not fit the models but fit reality perfectly. And our job, the only job worth doing, is to listen. So here we are, standing on a planet 4.5 billion years old, looking at light from an object that began its journey when the universe was barely 3 billion years old. Light that has been traveling toward us for longer than our sun has existed, longer than the Earth has been solid, longer than anything you can point to and call familiar. And that light carries a single undeniable message. The universe does not wait for permission. TON 618 should not exist, not by the rules we wrote, not by the timelines we calculated, not by the growth curves we trusted. And yet there it sits, 66 billion solar masses, shining so brightly that a telescope in Mexico caught its glow on a photographic plate in 1957, and someone catalogued it as star number 618. Not knowing, not suspecting, just recording, another faint point of light in an infinite sky. 15 years later, someone looked closer, and the faint star became a quasar, and the quasar became a monster, and the monster became a question that the field is still trying to answer. How does a black hole this massive form this early? What does it mean that the infant universe was capable of building something we thought required billions more years? And what else are we getting wrong? James Webb is showing us the answer. Not in words, in objects. More massive black holes at impossible distances. More galaxies assembled too soon. More structures that break the models we spent decades building. TON 618 is not an outlier. It is a preview, a signal from an era when the cosmos was doing things we have not accounted for. Growing faster, building larger, operating under conditions that no longer exist and that we are only now beginning to glimpse. The map is not the territory. The models are not reality. And the moment we forget that is the moment we stop learning. TON 618 is still out there, receding, isolated, unreachable, a memory written in light, a signal from the edge of everything, still shining, still waiting, still asking the same question it asked the first time someone looked closely enough to see what it really was. How did this